Hey there, space explorers and cosmic curiosity seekers. Welcome back to the channel. If you're new here, I'm thrilled you've stumbled upon what might be the most mind-bending journey we'll ever take together. And if you're a returning subscriber, you know we don't just scratch the surface here. We dive deep into the mysteries that keep the greatest minds on our planet awake at night. Today, we're tackling something that sits at the very edge of human understanding, a question that's been whispered by philosophers, debated by theologians, and now pursued with mathematical precision by the world's most brilliant physicists. What happened before the Big Bang? I want you to pause for a second and really think about that. We've all heard about the Big Bang, that explosive moment 13.8 billion years ago when our entire universe burst into existence from a point smaller than an atom. But here's what they don't tell you in school. The Big Bang isn't actually the beginning. It's more like the first page of a book that's missing its preface. The theory itself breaks down if you try to push it back to time zero. You end up with what's called a singularity, a point of infinite density where all our physics equations throw up their hands and say, "We give up." That's not a satisfying answer. That's a signpost telling us there's more to the story. So today, we're going on an epic voyage beyond that barrier. We're going to explore every major theory physicists have developed about what came before our universe began. And I'm not going to just give you watered-down summaries. We're going deep into the mathematics, the philosophy, the cutting-edge research that, quite frankly, might break your brain just a little bit. But don't worry, I'll be your guide through this cosmic labyrinth, translating the most complex ideas into plain English that anyone can understand. We're going to look at cyclic universes that might have been bouncing forever, multiverses where our cosmos is just one bubble in an infinite foam, quantum fluctuations that might have birthed reality from what physicists call nothing, and mind-bending proposals where time itself loses its meaning. We'll examine the evidence, the criticisms, the heated debates dividing the scientific community, and the profound implications for our place in existence. By the end of this video, you'll have a comprehensive understanding of why the question, what came before the Big Bang, isn't just a philosophical whim. It's one of the most important scientific mysteries of our time. You'll learn why some physicists argue there's no before at all, while others insist our universe must be part of a much larger, perhaps eternal, cosmos. And you'll discover that the answer to this question touches on everything from the nature of time and space to the ultimate fate of everything that exists. So grab your favorite beverage, get comfortable, and maybe wrap your head in duct tape so it doesn't explode, because we're about to venture where few documentaries dare to go. This isn't just another space video. This is the deepest dive into cosmic origins you'll find anywhere on this platform. If you find your mind being blown, and trust me, it will be, do me a favor and hit that like button to let me know you're surviving the journey. If you want to join our community of cosmic explorers, smash that subscribe button and ring the notification bell so you never miss our deep dives into the universe's greatest mysteries. And here's something I really want to know from you. Drop a comment below telling me where in the world you're watching from and what time it is right now. I love seeing how this community spans every corner of the globe, from early morning coffee sippers to late-night stargazers. Your comments, your thoughts, your theories, they're what make this community special, so please share them. All right, are you ready? Let's begin our journey beyond the Big Bang. The story really starts with what we know for certain, or at least what we're pretty darn confident about. The Big Bang Theory, despite its name, isn't really about an explosion. It's about expansion. Think of it this way. Imagine you're watching a movie of the universe running backwards. You see galaxies flying apart, but as you rewind, they get closer together. The universe gets denser, hotter, and smaller. Go back far enough, about 13.8 billion years, and everything we can observe, all the hundreds of billions of galaxies, all the stars, all the matter and energy, everything collapses into a state of unimaginable density and temperature. This is what we call the Big Bang. The evidence for this is overwhelming and comes from multiple independent sources. First, there's Hubble's discovery in the 1920s that galaxies are moving away from us, and the farther away they are, the faster they're receding. This tells us space itself is expanding. Then in 1965, Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation, the afterglow of the Big Bang. This faint hiss of microwaves coming from every direction in space is literally the light from the early universe, stretched to longer wavelengths as space expanded over billions of years. It's like seeing the embers of a cosmic fire that burned 380,000 years after the beginning. The pattern of this radiation matches predictions from Big Bang models with stunning precision. We also have the abundance of light elements: hydrogen, helium, and lithium. Big Bang nucleosynthesis predicts exactly how much of each should have been forged in those first few minutes when the universe was hot and dense enough for nuclear fusion, and observations match those predictions beautifully. And then there's the large-scale structure of the universe, the way galaxies cluster into filaments and voids, which is exactly what you'd expect from tiny quantum fluctuation stretched to cosmic size by early expansion. So the Big Bang theory is remarkably successful. It explains the expanding universe, the cosmic microwave background, the light element abundances, and the origin of cosmic structure. But, and this is crucial, it has a major flaw. When you trace the expansion back to time zero, the equations of general relativity predict a singularity, a point of infinite density and infinite curvature of spacetime. This is a problem because infinities in physics usually mean the theory has broken down. The theory is telling us, I can't describe what happens here. It's like trying to divide by zero on a calculator. The calculator doesn't give you a secret answer, it just says error. The singularity is general relativity's way of saying error. Physicists have known for decades that general relativity can't be the final word. It describes gravity as the curvature of spacetime, and it works beautifully for stars, galaxies, and the large-scale universe. But it doesn't account for quantum mechanics, the strange rules that govern the subatomic world. In the extreme conditions of the early universe, where distances are incredibly tiny and densities are enormous, quantum effects must have been important. We need a theory of quantum gravity to really understand what happened. So the search for what came before the Big Bang is really a search for a quantum theory of gravity that can describe the universe when it was so small that quantum mechanics and general relativity both mattered. This is the holy grail of theoretical physics. String theory is one approach, loop quantum gravity is another, and there are several others. Each of these theories suggests dramatically different possibilities for cosmic origins. Let's start with one of the most mind-bending ideas, that our universe might be just one bubble in an infinite multiverse, born from a process called eternal inflation. This theory, pioneered by Alan Guth, Andre Lind, and others in the 1980s, starts with a simple question. Why is the universe so uniform? When we look at the cosmic microwave background, we see that the temperature is almost exactly the same everywhere, about 2.725 degrees above absolute zero. But regions of the universe on opposite sides of the sky are so far apart that light hasn't had time to travel between them since the Big Bang. So how did they know to be at the same temperature? This is called the horizon problem. Inflation solves this by proposing that the very early universe, we're talking about a tiny fraction of a second after the traditional Big Bang, perhaps around 10 seconds, went through an extraordinary period of exponential expansion. In less than a blink of an eye, the universe doubled in size at least 80 times, maybe many more. This means that tiny regions that were once in contact with each other, able to exchange heat and reach the same temperature, were suddenly stretched to enormous distances. The smoothness we see today is because everything originated from a single tiny patch that had time to equalize before inflation ripped it apart. Inflation also solves another puzzle called the flatness problem. According to general relativity, spacetime can be curved. It could be positively curved like the surface of a sphere, negatively curved like a saddle, or flat like a sheet of paper. Observations show our universe is remarkably flat, to within about 0.4% margin of error. But for the universe to be this flat today, it had to be fantastically flat at the beginning. The odds of this happening by chance are astronomically small. Inflation explains this because no matter how curved spacetime was initially, stretching it by an enormous factor smooths it out, just like blowing up a balloon makes a small patch of its surface look flat. But here's where it gets really wild. In most versions of inflation, the process doesn't stop everywhere at once. Think of a pot of water boiling. Bubbles of steam form, expand, and rise. In eternal inflation, the universe undergoes a similar process. The scalar field that drives inflation, called the inflaton, gets stuck in a high-energy state that keeps inflating. But quantum fluctuations cause some regions to drop out of inflation, like bubbles forming in the boiling water. Each bubble becomes a universe like ours, while the space between bubbles keeps inflating forever, creating more bubbles. So in this picture, our Big Bang wasn't the beginning of everything. It was just the end of inflation in our particular bubble. There could be an infinite number of other bubbles, each a separate universe with its own laws of physics. Some might have different numbers of dimensions, different kinds of particles, different fundamental constants. In fact, the laws of physics themselves might be determined by how the inflaton field fluctuated when each bubble formed. This creates what's called a landscape of possible universes, a multiverse where every possible combination of physical laws exists somewhere. The implications are staggering. If eternal inflation is correct, then there are infinitely many universes, and among that infinity, every possible configuration of matter and energy will occur infinitely many times. There could be exact copies of you watching this video in other universes. There could be universes where the Big Bang happened slightly differently, where stars never formed, where life never emerged. The reason we find ourselves in a universe that supports life isn't because the universe was designed for us. It's because we could only exist in a universe that supports life. This is called the anthropic principle. But eternal inflation isn't without its problems. For one thing, it's extremely difficult to test. By definition, these other universes are causally disconnected from ours. We can never observe them directly. Some critics, including the legendary physicist Roger Penrose, argue that eternal inflation is too flexible. It can be tweaked to explain almost anything, which makes it less scientifically rigorous. Penrose has pointed out that the measure problem is severe. In an infinite multiverse, how do you calculate the probability of observing any particular feature? The answer depends on how you define most universes, and there's no consensus on the right way to do this. Moreover, eternal inflation still doesn't solve the ultimate origin question. It pushes the Big Bang back, but you still have to ask, what set up the inflaton field in the first place? What caused inflation to start? Some physicists argue that the inflaton field could have emerged from quantum fluctuations in a primordial vacuum, but that just pushes the question back another step. It's turtles all the way down. Let's turn to a radically different idea, that our universe might be part of an eternal cosmic cycle, with no beginning and no end. This concept of cyclic cosmology has ancient roots. Many cultures imagine time as a wheel, but modern physics has given it new mathematical precision. There are several versions, but they share a common theme. The Big Bang wasn't a unique event, but one in a potentially infinite series of expansions and contractions. One of the most developed cyclic models is the ekpyrotic universe, based on string theory. String theory proposes that the fundamental ingredients of nature aren't point particles but tiny vibrating strings of energy. It also requires extra dimensions of space beyond the 3 we experience, possibly 10 or 11 dimensions total. In this framework, our entire 3-dimensional universe could be a brane, a membrane floating in a higher dimensional space. Think of it like a sheet of paper floating in a room, except the room has extra dimensions we can't perceive. The ekpyrotic model proposes that what we call the Big Bang was actually the collision between our brain and another brain in this higher dimensional space. Before the collision, the universe was in a slow contracting phase. The brains were drawn together by a spring-like force, and as they approached, quantum fluctuations created tiny ripples in the brains. When they collided, the kinetic energy of the collision was converted into the hot, dense matter and radiation of the Big Bang. The ripples from before the collision became the seeds of galaxy formation we see in the cosmic microwave background. This is profoundly different from inflation. Instead of a brief burst of superfast expansion from a tiny point, the ekpyrotic model suggests a slow contraction that bounces into expansion. The universe could be much older than 13.8 billion years, potentially infinite in age, going through cycle after cycle of contraction and expansion. Each cycle starts with a Big Bang, expands for billions of years, eventually contracts in a big crunch, and then bounces back into a new Big Bang. The ekpyrotic model has some advantages over inflation. It doesn't require a singularity. The equations can be worked out right through the bounce. It also provides a different explanation for the patterns we see in the cosmic microwave background. However, it faces its own challenges. For one, the collision between brains has to be extremely fine-tuned to produce the right kind of ripples. Also, the model relies on string theory, which, despite decades of work, hasn't been experimentally confirmed, and the extra dimensions required by string theory have never been observed. But the biggest challenge came in 2001, when physicists showed that the original ekpyrotic model couldn't produce the right spectrum of fluctuations to match observations. The ripples it produced were too blue. They had more power at small scales than large scales, which is opposite to what we observe. However, theorists have since developed new versions of the model that might solve this problem. The cyclical model, developed by Paul Steinhardt and Neil Tirach, modifies the ekpyrotic idea to include a period of slow acceleration at the end of each cycle, which could produce the right pattern of fluctuations. Despite these improvements, many cosmologists remain skeptical. The model is mathematically complex, and it's not clear that it offers a better explanation than inflation for the observations. Plus, it still doesn't solve the ultimate origin question. If the universe cycles forever, you can ask, is there a beginning to the cycles, or have they always existed? Some versions suggest the cycles could be infinite in both directions, no beginning, no end. But that raises philosophical questions about what always even means. Speaking of infinite cycles, let's talk about one of the most controversial and fascinating proposals, Roger Penrose's conformal cyclic cosmology, or CCC. Penrose, a Nobel Prize winner for his work on black holes, has spent decades developing a theory that our universe is just one eon in an infinite sequence of universes, each separated by what he calls a crossover surface. The key insight behind CCC is something called conformal invariance. In physics, some equations stay the same if you multiply all the distances by a scale factor. The equations of light, for example, are conformally invariant. Penrose realized that as the universe ages, it becomes increasingly dominated by massless particles like photons and gravitational waves. Massive particles like electrons and protons will eventually decay, and black holes will evaporate via Hawking radiation. As this happens, the universe loses track of its scale. The distinction between big and small becomes meaningless. In the far, far future, after all the stars have burned out, all the black holes have evaporated, and the universe has expanded into a cold, dark, empty void, it becomes mathematically identical to the intense, hot, dense state at the beginning of a new universe. The infinite future of one eon becomes the Big Bang of the next. The crossover between eons is smooth because the mathematics are the same. It's just a matter of perspective. Penrose suggests that there might be observational evidence for CCC in patterns in the cosmic microwave background. He claims to have found Hawking points, circles in the CMB, where the temperature fluctuations are slightly lower than average. These, he argues, could be the imprint of supermassive black holes from the previous eon, their Hawking radiation patterns surviving the crossover into our universe. When Penrose first proposed these ideas, they were met with considerable interest. The mathematics is elegant, and the idea that the far future could become a new beginning is poetic. But the observational claims have been heavily criticized. Multiple independent analyses of the CMB data, particularly from the Planck satellite, have found no evidence for these Hawking points. Critics argue that what Penrose identified as special circles are just random fluctuations that you'd expect in any map of the CMB. Statistical analyses show that the features aren't significant. They're not robust against different ways of analyzing the data. The physics community has largely rejected the observational claims for CCC. Hundreds of scientists have pointed out that the predictions are refuted by the data, and that the claimed features only appear if you analyze the data in scientifically questionable ways. Penrose continues to defend his ideas, but most cosmologists remain unconvinced. However, the mathematical framework of CCC remains interesting. Even if the specific observational predictions don't hold up, the idea that the universe might reset itself through conformal invariance is still being explored. Some physicists are looking at whether modifications to the theory could produce different observable signatures that might survive scrutiny. But for now, CCC remains on the fringe of mainstream cosmology. Now let's explore a theory that comes from a completely different approach to quantum gravity: loop quantum cosmology and the Big Bounce. Loop quantum gravity, or LQG, is an alternative to string theory. While string theory says the fundamental building blocks are one-dimensional strings, LQG takes a different approach. It tries to quantize spacetime itself. The central idea is that space isn't continuous. It's made of discrete chunks, like pixels on a computer screen. These are called atoms of space. The theory uses mathematical objects called spin networks to describe how these chunks are connected. When you include time, you get spin foams, a dynamic web of quantum geometry. When physicists apply LQG to cosmology, something remarkable happens. The singularity at the Big Bang disappears. Instead of a point of infinite density, you get a quantum bounce. The universe before the bounce was contracting, getting smaller and denser. But when it reached the Planck density, about a billion trillion 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 times the density of water, quantum effects become so strong that gravity becomes repulsive instead of attractive. The collapse stops and reverses into expansion. The Big Bang is just the moment of transition. This is profoundly different from both inflation and cyclic models. There's no inflatened field, no extra dimensions, no collision between branes. It's just the quantized geometry of spacetime itself that causes the bounce. The universe could be infinite in age, going through cycle after cycle of contraction and expansion. Each cycle would start with a bounce, expand for billions of years, eventually contract and bounce again. The Big Bounce model has some attractive features. It naturally avoids the singularity problem. It can produce the right kind of density fluctuations to match observations, though the details are still being worked out. And it's based on loop quantum gravity, which some physicists find more compelling than string theory because it doesn't require extra dimensions or supersymmetry. But LQG faces its own challenges. The theory is mathematically complex and hasn't been fully worked out. We don't yet know how to incorporate matter and radiation in a completely satisfactory way. And like other theories of quantum gravity, it lacks experimental confirmation. Some of its predictions, like modifications to the speed of light at very high energies, are being tested by observing gamma-ray bursts from distant galaxies, but so far no deviations have been found. Moreover, even if the Big Bounce is real, it still raises the eternal question: what set up the previous contracting phase? The bounce could be part of an infinite cycle, but that doesn't necessarily answer the ultimate origin question. It might just push it back further. Now let's discuss one of the most counterintuitive proposals, that there might be no before at all because time itself started at the Big Bang. This is the Hartle-Hawking no-boundary proposal, developed by Stephen Hawking and James Hartle in the 1980s. Hawking approached the problem by applying quantum mechanics to the entire universe. In quantum theory, a particle doesn't follow a single path from point A to point B instead. It takes all possible paths simultaneously, each with a certain probability. This is Richard Feynman's sum over histories approach. Hawking and Hartle asked, what if we apply this to the universe as a whole? What if the universe doesn't have a single history, but a sum over all possible histories? They proposed that near the Big Bang, the distinction between space and time becomes blurred. Using a mathematical trick called imaginary time, where time is treated like another dimension of space, they showed that you could have a universe with no boundary, no edge, no starting point. The history of the universe would be like the surface of a sphere. Asking what happened before the Big Bang would be like asking what's south of the South Pole. The question itself is meaningless because before loses its meaning. In this picture, the early universe emerged from a fuzzy quantum state where time as we know it didn't exist. The universe didn't come from nothing. It came from a state where there was no time for anything to be before. The laws of physics would be the same at every point on this spherical geometry, so there would be no special starting point where the laws break down. The no-boundary proposal was revolutionary. It provided a way to talk about quantum creation without invoking a singularity. It suggested that the universe could be finite in imaginary time but infinite in real time. And it made predictions. It naturally leads to inflation, and it predicts a specific spectrum of density fluctuations. But the proposal has faced significant criticism. The mathematics is extremely challenging, and it's not clear that the predictions are unique. In 2017, physicists Job Feldbrug, Jean-Luc Leiners, and Neil Turok applied new mathematical techniques to the no-boundary proposal and concluded that it actually fails to predict our universe. They argued that the wave function of the universe, that Hawking and Hartle derived, would lead to an almost empty universe, not the rich, structured cosmos we observe. Hawking and Hertog responded to these criticisms by refining the theory, suggesting that you need to restrict the sum over histories to only those that are consistent with observations, a principle they called top-down cosmology. But many physicists find this approach unsatisfying because it seems circular. You're using observations to restrict the theory that should predict those observations. Moreover, the use of imaginary time is controversial. While it's a powerful mathematical tool in quantum mechanics, it's not clear it has physical meaning when applied to cosmology. The proposal also struggles with the measure problem. How do you assign probabilities to different universes in the wave function? Despite these challenges, the no-boundary proposal remains influential because it offers a philosophically elegant solution to the origin problem. It suggests that the universe doesn't need a cause in the traditional sense because there's no time for a cause to act in. The universe simply is, and our experience of time emerges from quantum correlations within it. Now let's explore another approach that focuses on quantum fluctuations in a primordial vacuum, literally trying to get a universe from nothing. The idea that the universe might be a quantum fluctuation goes back to physicist Edward Tryon in 1973. He proposed that if you start with a quantum vacuum, a state of empty space allowed by quantum mechanics, and if that vacuum has zero total energy, then a fluctuation could produce a universe without violating any physical laws. This sounds crazy, but quantum mechanics allows for temporary violations of energy conservation on extremely short timescales. Virtual particles pop in and out of existence all the time in empty space. The universe itself could be a similar kind of fluctuation, just on a much larger scale, and sustained by the fact that its total energy is exactly zero. How could the universe have zero energy? It turns out that the gravitational potential energy of all the matter in the universe might be exactly balanced by its positive mass energy. In general relativity, gravitational energy is negative. It takes work to pull things apart against gravity. If you add up all the mass energy in the universe and subtract the gravitational energy, you might get zero. In that case, the universe is like a free lunch. You can create it from nothing without violating energy conservation. This idea was developed further by physicists like Alexander Vilenkin and James Hartle in the 1980s. Vilenkin proposed that quantum tunneling could create a universe from nothing. In quantum mechanics, a particle can tunnel through a barrier that it classically couldn't cross. Similarly, a tiny patch of space could tunnel from nothing into an inflating universe. The nothing here isn't absolute nothingness. It's a quantum state with no matter, no radiation, no classical spacetime. But it still has quantum mechanical properties, including uncertainty. From this quantum foam, a universe could spontaneously appear. The probability of this happening might be extremely small, but in a timeless quantum state, even extremely improbable events will eventually happen. This approach has some appealing features. It doesn't require any pre-existing universe or cycles. It suggests that the laws of quantum mechanics themselves might be enough to create a universe, and it can be connected to inflation. The quantum fluctuation that created the universe could have set up the conditions for inflation to begin. But it also raises deep questions. What determines the laws that govern the quantum vacuum? Are those laws themselves something that needs to be explained? The proposal also struggles with the same measure problems as other quantum cosmology approaches, and like the no-boundary proposal, it's extremely difficult to test observationally. Some physicists argue that this approach doesn't really solve the origin problem, it just moves it to a different level. Instead of asking, where did the universe come from? You're asking, where did the quantum vacuum come from? Or why do the laws of quantum mechanics exist? The Nobel laureate Frank Wilczek once quipped, the answer to the ancient question, why is there something rather than nothing, would be that nothing is unstable. Now, let's step back and consider what all these theories have in common and where they diverge. Each represents a different approach to solving the same fundamental problem. General relativity predicts a singularity, but we know that can't be the final answer. The approaches differ in how they modify gravity at the quantum scale. Inflationary models, both single universe and eternal, keep general relativity but add a new field, the inflaton, that drives a period of rapid expansion. They preserve the basic structure of spacetime but modify the early universe's dynamics. The singularity is still there in the equations, but inflation happens after it, so we don't need to resolve it to explain observations. Cyclic and ekpyrotic models replace the Big Bang singularity with a bounce. They modify gravity at high densities, either through extra dimensions and brane collisions or through quantum effects, to make gravity repulsive at extremely short distances. This avoids the singularity entirely and suggests an eternal cosmic cycle. Loop quantum gravity approaches quantized spacetime itself, making geometry discrete. This naturally eliminates the singularity and replaces it with a bounce. The Big Bang becomes a transition in a much longer history. String theory approaches like the ekpyrotic model suggest new degrees of freedom, extra dimensions and branes, that change the story of cosmic origins. The singularity might be an artifact of our limited three-dimensional perspective. The no-boundary and quantum fluctuation approaches take a more radical step. They treat the entire universe quantum mechanically, describing its origin with a wave function. Rather than modifying spacetime at the singularity, they suggest that spacetime itself emerges from an underlying quantum state. Each of these approaches has its champions and its critics. The inflationary paradigm, particularly eternal inflation, is currently the most popular among cosmologists. This is partly because it makes predictions that have been confirmed by observations of the cosmic microwave background, particularly the pattern of temperature fluctuations. Inflation predicts that these fluctuations should be nearly scale invariant, having the same power on all scales, and Gaussian, having a particular statistical distribution, which is exactly what we see. But critics like Penrose argue that inflation is too flexible. It can be adjusted to explain almost any observation, which some argue makes it less predictive. Penrose points out that inflation requires extremely special initial conditions itself. The inflatoned field has to be in a very particular state. So rather than solving the fine-tuning problem, inflation just moves it to a different level. The observational situation is complex. The cosmic microwave background observations by COBE, WMAP, and Planck satellites have confirmed many predictions of inflation. They've measured the spectral index, a measure of how the fluctuations change with scale, to high precision, and it matches inflationary predictions. They've also measured the polarization of the CMB, which can reveal evidence of gravitational waves from inflation. So far, we haven't detected the primordial gravitational waves that many inflation models predict, but the search continues. However, these observations don't uniquely prove inflation. Other models, particularly the cyclic and ekpyrotic models, have been developed to produce similar predictions. The cyclic model can also generate nearly scale-invariant fluctuations, though the mechanism is different. In inflation, fluctuations are created by quantum effects during the rapid expansion. In cyclic models, they're created by quantum fluctuations in the contracting phase before the bounce. The key difference is in the gravitational wave signal. Many inflation models predict a strong signal of primordial gravitational waves, which would leave a distinctive pattern in the polarization of the CMB. So far, this hasn't been detected, which has allowed cyclic models to remain competitive. But future observations with more sensitive instruments might finally detect these gravitational waves and confirm inflation, or rule out many inflation models. The other theories face more severe observational challenges. Penrose's claims about Hawking points have been thoroughly debunked by multiple independent analyses. The Planck satellite data shows no evidence for concentric circles or other features that would support CCC. Loop quantum cosmology makes predictions about modifying the propagation of light at high energies, which could be tested by observing gamma-ray bursts from distant galaxies. If spacetime is discrete, then higher-energy photons should travel slightly slower than lower-energy photons. But so far, no such effect has been observed. The no-boundary proposal and quantum fluctuation approaches are even harder to test. They make predictions about the wave function of the universe, but these predictions depend on how you define the sum over histories. Different choices can lead to different predictions, making it hard to test the core idea. Some physicists have suggested looking for signatures in the CMB that might distinguish between different quantum cosmology models, but this is speculative. The philosophical implications of these theories are profound. If eternal inflation is correct, our universe is just one of infinitely many, and the question why this universe is answered by the anthropic principle. But this raises questions about the nature of probability in an infinite ensemble. In an infinite multiverse, every possible event happens infinitely many times, so how do you assign probabilities? This is the measure problem. If cyclic models are correct, the universe might be eternal, with no ultimate beginning. This avoids the need for a creation event. But it raises its own philosophical questions about the nature of time and causality in an eternal cosmos. If quantum cosmology approaches are correct, then the universe might be self-contained, with no need for external cause. The laws of physics themselves might explain why there is something rather than nothing. But this raises the question, why these laws? Why does quantum mechanics have the structure it does? Some physicists suggest that the laws themselves might be determined by deeper principles, like the requirement that the universe be logically consistent. Others suggest that all possible mathematical structures exist, and we find ourselves in one that supports observers, the mathematical universe hypothesis proposed by Max Tegmark. The debate between these viewpoints is ongoing and often heated. Inflationary cosmologists like Alan Guth, Andre Linde, and Paul Steinhardt, though Steinhardt later became a critic of inflation and champion of cyclic models, have argued for decades about the details. String theorists and loop quantum gravity researchers debate the merits of their approaches. Philosophers weigh in on the implications. What's clear is that we don't yet have a definitive answer. The physics community is divided, and the observational evidence, while increasingly precise, hasn't yet been able to distinguish between many of these theories. The singularity problem remains unsolved. But there are reasons for optimism. New experiments are coming online that could break the deadlock. The Simons Observatory and CMB-S4 will map the cosmic microwave background with unprecedented precision, potentially detecting primordial gravitational waves or other subtle features that could differentiate inflation from cyclic models. Gravitational wave observatories like LIGO and Virgo, and future space-based detectors like LISA, might detect signals from the early universe. Particle accelerators are searching for new physics that could reveal supersymmetry or extra dimensions, and new theoretical developments continue to refine these models. There's also a growing recognition that we might need to think differently about what counts as evidence. In a multiverse scenario, direct observation of other universes might be impossible, but we might still infer the multiverse's existence if it's the best explanation for the properties of our universe. This is similar to how we infer the existence of other planets or black holes by their effects on what we can observe. The question of what came before the Big Bang also intersects with deep questions in philosophy and even theology. For millennia, humans have wondered about the ultimate origin of everything. Many religious traditions posit a creator deity who exists outside of time and space. The scientific theories we've discussed offer naturalistic alternatives, but they don't necessarily rule out theological interpretations. Some theologians have embraced inflation, suggesting that the inflatened field could be the mechanism by which a creator brought the universe into being. Others see the eternal or cyclic universe as compatible with certain philosophical or religious worldviews. But from a strictly scientific perspective, the goal is to develop theories that are testable, predictive, and elegant. The best theory will be the one that explains the most with the fewest assumptions, matches observations, and makes predictions that can be verified or falsified by future experiments. Let's dive deeper into some of the mathematical and conceptual challenges these theories face, because understanding the difficulties helps appreciate why this problem has remained unsolved for so long. The central issue is that we're trying to apply quantum mechanics, which normally describes particles and fields within spacetime, to spacetime itself. This creates conceptual puzzles that physicists are still grappling with. In quantum mechanics, we describe a system using a wave function which evolves in time according to the Schrödinger equation. But if the system is the entire universe, what does the wave function evolve in relation to? There's no external clock, no outside observer. This is the problem of time in quantum cosmology. Different approaches solve this in different ways. In the canonical quantization approach used in loop quantum gravity, you treat time differently from space and try to define a clock within the universe itself, like the value of a scalar field. But this leads to complications because different choices of clock give different quantum theories. In the path integral approach used in the no-boundary proposal, you treat space and time more symmetrically. You sum over all possible geometries of spacetime that have certain boundary conditions. The wave function of the universe gives the probability for different configurations, but defining the sum over all geometries is mathematically tricky. There are infinitely many possibilities, and it's not clear how to weight them. The singularity problem manifests differently in each approach. In classical general relativity, the singularity is a point where curvature and density become infinite. In quantum approaches, you typically expect that quantum effects become important at the Planck scale, when densities reach about 1096 kilograms per cubic meter and distances shrink to 1035 meters. At this scale, our classical picture of smooth spacetime should break down and be replaced by quantum geometry. String theory approaches this by suggesting that spacetime emerges from more fundamental objects. At very small scales, the concept of a point becomes meaningless because strings have a finite size. The singularity is smeared out by stringy effects. The ekpyrotic model uses this to avoid the singularity. The brane collision isn't a point of infinite density. It's a transition mediated by string physics. Loop quantum gravity takes a more direct approach. It quantizes the geometry itself. The result is that areas and volumes come in discrete chunks. When you apply this to cosmology, the Big Bang singularity is replaced by a bounce because the quantum geometry has a minimum possible volume. The equations remain finite through the bounce. But both string theory and LQG face the challenge of making unique predictions that can be tested. Both have free parameters that can be adjusted, and both have struggled to reproduce the precise details of the cosmic microwave background as well as inflation does. The challenge of testing these theories can't be overstated. The energies involved in quantum gravity are absurdly high, far beyond what we can achieve in particle accelerators. To probe the Planck scale directly, you'd need a particle accelerator the size of a galaxy. So instead, we look for indirect signatures. One approach is to look for imprints in the cosmic microwave background. During inflation, quantum fluctuations in the inflatoned field were stretched to cosmic scales and became the seeds of structure. Different inflation models predict slightly different patterns of these fluctuations. By measuring the CMB with high precision, we can constrain which models are possible. Similarly, different quantum gravity models predict different corrections to the standard picture. Loop quantum gravity might modify the dispersion relation for light. Different frequencies might travel at slightly different speeds. This could be detected by looking at the arrival times of different energy photons from gamma-ray bursts. String theory might produce cosmic strings, vast one-dimensional defects in spacetime that would leave distinctive gravitational lensing patterns. Another approach is to look for gravitational wave signatures. Inflation predicts a background of primordial gravitational waves, which are ripples in spacetime itself. These would leave a distinctive B-mode polarization pattern in the CMB. So far, we haven't detected these B-modes, which has ruled out some simple inflation models but left many others viable. Cyclic and ekpyrotic models predict a much weaker gravitational wave signal, so if we do detect primordial B-modes with significant amplitude, that would be strong evidence for inflation and against cyclic models. Conversely, if we don't detect them even with increasingly sensitive experiments, that might favor cyclic models. The search is ongoing. Experiments like BICEP, the Simons Observatory, and the proposed CMB-S4 experiment are pushing the limits of sensitivity. They might detect the gravitational wave background within the next decade, which would be a game changer for cosmology. But what if we never find a definitive answer? What if these theories all make predictions that are too subtle to distinguish with any foreseeable technology? This is a real possibility that physicists are starting to grapple with. Some argue that if a theory can't be tested even in principle, it's not science, it's philosophy or metaphysics. Others argue that we should accept cosmological theories based on their theoretical elegance and explanatory power, even if direct empirical tests are impossible. This debate touches on the very nature of science. Traditionally, science proceeds by making predictions and testing them. But when we're dealing with the origin of everything, maybe we need to expand our notion of what counts as evidence. The string theorist David Gross has argued that the universe is the way it is because it is the only logically consistent possibility. If we could prove mathematically that only one set of physical laws is mathematically self-consistent, that might count as a kind of evidence. Others, like the physicist Carlo Rovelli, argue that we should focus on what we can measure and accept that some questions might remain beyond our grasp. The universe might have a beginning, or it might be eternal. We might never know for sure. But we can still build theories that explain what we can observe and make testable predictions about future observations. The philosophical implications of each theory are worth exploring in more detail. The eternal inflation multiverse suggests a vast, perhaps infinite, reality where everything that can happen does happen. This is both exhilarating and unsettling. It means our universe isn't special, it's just one of infinitely many. The fine-tuning that allows life to exist is explained by selection bias. We could only find ourselves in a universe that supports life. But this leads to the measure problem. In an infinite multiverse, how do you define probability? Every possible event happens infinitely many times, so counting doesn't work. Some physicists have proposed measure prescriptions that try to define probabilities by counting events in a specific way. For example, you might count events per unit volume, or per unit time, or using some other scheme. But different prescriptions give different answers, and there's no consensus on which is right. This has led some to question whether the multiverse is scientific at all. If you can't make unique predictions, is it falsifiable? The cyclic universe offers a different philosophical picture. Instead of infinite parallel universes, we have infinite sequential universes. Time is truly eternal, with no beginning or end. This resonates with some philosophical and religious traditions that see time as cyclical, but it also raises questions about causality and information. If the universe cycles forever, do the same events repeat? Does information survive from one cycle to the next? In some cyclic models, entropy increases from cycle to cycle, which means the cycles get longer and longer. This suggests that while the cycles might be infinite into the future, there might have been a first cycle in the past, a beginning after all. The loop quantum gravity picture suggests a more fundamental reality of discrete spacetime atoms. This is a radical departure from our intuitive picture of continuous space and time. If spacetime is quantized, then many of our philosophical concepts about infinity and continuity might need revision. It suggests that the universe is fundamentally discrete at the Planck scale, which could have implications for everything from the nature of time to the ultimate limits of computation. The quantum fluctuation picture suggests that the universe emerged from a state of nothing, though nothing in quantum mechanics is still something. It's a state with no matter or radiation but with quantum mechanical properties. This raises deep questions about the nature of nothing. Is a true philosophical nothingness even possible? Or is the quantum vacuum the simplest possible state, the bedrock of reality from which everything emerges? The Hartle-Hawking no-boundary proposal offers perhaps the most radical philosophical shift. It suggests that time itself is emergent, not fundamental. The universe doesn't evolve in time. Rather, time emerges from correlations within a static quantum state. This is reminiscent of some ideas in Eastern philosophy and modern physics about the illusion of time. If time isn't fundamental, then questions about before and after might be misguided. The universe simply exists as a four-dimensional spacetime manifold, and our consciousness experiences it sequentially. Each of these philosophical perspectives has profound implications for how we see ourselves and our place in the cosmos. If eternal inflation is true, we're infinitesimal specks in an infinite sea of universes. If cyclic models are true, we're part of an eternal cosmic dance. If loop quantum gravity is true, we're patterns in a fundamental quantum geometry. If the universe is a quantum fluctuation, we're the product of the most fundamental random process. And if the no-boundary proposal is true, we're part of a self-contained, causeless reality. Let's examine some of the specific technical challenges these theories face, because understanding the difficulties helps us appreciate why progress has been slow. One major challenge is the problem of quantum backreaction. When you have quantum fields in a curved spacetime, the quantum fluctuations affect the spacetime geometry, and the geometry affects the quantum fields. This is a viciously complex feedback loop that's extremely difficult to calculate. In inflationary models, we usually treat the inflatoned field quantum mechanically, but treat spacetime classically, a semi-classical approximation. This works well enough to make predictions, but it's not fundamentally consistent. A full quantum gravity treatment would need to quantize both the matter fields and spacetime itself. This is extraordinarily difficult, which is why we don't have a complete theory of quantum cosmology yet. Another challenge is the problem of renormalization. In quantum field theory, when you calculate loop corrections to processes, you often get infinite results. The theory provides a procedure called renormalization to absorb these infinities into redefinitions of physical parameters. But when you try to apply this to quantum gravity, the infinities are worse and can't be renormalized in the usual way. String theory solves this by having a built-in cutoff at the string scale. Loop quantum gravity solves it by making spacetime discrete. But both approaches run into difficulties when trying to reproduce the successes of quantum field theory in the low-energy limit. The problem of initial conditions is also thorny. Inflation can explain why the universe is uniform and flat, but it requires the inflatoned field to start in a particular state. In chaotic inflation models, Andre Linde proposed that the inflatoned field could have different values in different regions, leading to eternal inflation. This helps with the initial conditions problem because you don't need the whole universe to start in the right state, just some patch of it. But it still raises questions about what determined the distribution of initial field values. In cyclic models, the initial conditions problem is different. The universe cycles forever, so you might think you don't need initial conditions, but you still need to explain why the universe has the properties it does. Why does the bounce happen at the Planck density? Why do the cycles have the properties they do? Some cyclic models have attractor solutions, trajectories that the universe tends to follow regardless of small variations. This would make the cycles robust and perhaps independent of initial conditions. But it's not clear if these attractors really exist in realistic models that include matter and radiation. The measure problem in eternal inflation is perhaps the most severe conceptual difficulty. In an infinite multiverse, there are infinitely many observers, infinitely many planets, infinitely of everything. How do you compare probabilities? If there are infinite copies of you in the multiverse, what does it mean to say that a particular event is probable? Different ways of defining probabilities give wildly different answers. Some physicists have proposed using the holographic principle to define a measure. The idea is that you count events on a boundary at infinity rather than in the bulk spacetime. This can give finite answers even when the volume is infinite. But these proposals are still controversial, and it's not clear if they give physically reasonable results. Another technical challenge is the problem of backreaction in eternal inflation. The quantum fluctuations that drive eternal inflation are extremely small, but over time they can accumulate and affect the overall expansion. Calculating this backreaction properly is very difficult, and it's not clear that the approximations used in most inflation models are valid. In loop quantum cosmology, one challenge is connecting the quantum description near the bounce to the classical description we observe. The universe today is extremely well described by classical general relativity. How does the quantum geometry of the bounce give rise to this classical behavior? This is the problem of quantum to classical transition, and it's a major focus of current research. There's also the challenge of incorporating inhomogeneities. Most quantum cosmology models start by assuming the universe is perfectly uniform, a huge simplification. But we know the real universe has structure. Extending these models to include fluctuations and understand how they evolve through the bounce is extremely difficult. Recent progress has been made, but it's still an active area of research. Let's also discuss some of the more speculative and recent proposals that push the boundaries even further. One fascinating idea is the mathematical universe hypothesis proposed by Max Tegmark. He suggests that the ultimate reality is mathematical structure, and that all mathematical structures exist physically. In this view, the question, why this universe, is answered by saying that all possible universes exist, and we're in one that supports observers. This is the ultimate multiverse theory. It doesn't just posit multiple universes with different physical constants, but multiple universes with completely different mathematical structures and even different fundamental equations. This idea is extremely controversial and difficult to test. It's more philosophy than science, according to many critics, but it raises interesting questions about the nature of reality and the relationship between mathematics and physics. Another speculative idea is the simulation hypothesis, the notion that our universe might be a computer simulation run by an advanced civilization. While this might sound like science fiction, some physicists have taken it semi-seriously and asked what observable signatures a simulation might have. For example, there might be a minimum length scale or a maximum energy, like the resolution limit of a computer screen. Some have suggested that the high-energy cosmic rays we observe might show signs of a lattice structure. So far, no such evidence has been found, but it's an interesting thought experiment that highlights how we might test seemingly untestable ideas. There's also the holographic universe idea, which suggests that all the information in a volume of space can be encoded on its boundary. This emerges from string theory and black hole physics. Some researchers have suggested that the Big Bang might be understood as a projection of information from a lower dimensional boundary. This is highly speculative, but has led to interesting mathematical results that might apply to cosmology. Let's talk about some of the experimental efforts that might break this stalemate. The cosmic microwave background has been our most powerful tool so far, but future observations will be even more precise. The Simons Observatory, currently under construction in Chile, will map the CMB with 10 times the sensitivity of Planck. It might detect the primordial B-mode polarization that would be a smoking gun for inflation. The proposed CMB-S4 experiment would be even more powerful, using telescopes at both the South Pole and in Chile to create a detailed map of the microwave sky. If these experiments detect primordial gravitational waves with the specific properties predicted by inflation, particularly a ratio of tensor to scalar fluctuations above about 0.01, that would be strong evidence for inflation and against most cyclic models. But if they don't detect these waves, or if they detect a different pattern than inflation predicts, that could open the door to alternative models. Gravitational wave astronomy is another promising avenue. The LIGO and Virgo detectors have opened a new window on the universe, detecting gravitational waves from merging black holes and neutron stars. Future space-based detectors like LISA will be sensitive to much lower frequencies and could detect gravitational waves from the early universe. These might reveal features of quantum gravity or the nature of the Big Bang itself. Particle physics experiments are also relevant. The Large Hadron Collider has searched for supersymmetry and extra dimensions, but hasn't found them yet. Future colliders, like the proposed Future Circular Collider, might reach higher energies and discover new physics that could point toward string theory or other quantum gravity approaches. There's also the possibility of observing quantum gravity effects directly in astrophysical phenomena. Gamma-ray bursts emit photons across a wide range of energies. If spacetime is discrete, higher energy photons should travel slightly slower, causing a spread in arrival times. The Fermi Gamma Ray Space Telescope has looked for this effect and hasn't found it, but future observations might be more sensitive. Quantum computing might also offer new ways to simulate quantum gravity models. Some physicists have proposed using quantum computers to simulate the quantum geometry of spacetime, potentially revealing signatures that could be looked for in observations. Let's also discuss the role of philosophy in guiding these scientific efforts. While physics is ultimately an empirical science, philosophy helps frame the questions and interpret the answers. The question, what came before the Big Bang, is itself philosophical. It assumes there's a meaningful notion of before. The Hartle-Hawking proposal challenges this assumption, suggesting that time itself might be emergent. Philosophical principles like Occam's razor, the idea that simpler explanations are preferred, often guide theory selection. Eternal inflation is popular partly because it seems like a natural consequence of simple inflation models. But critics argue that an infinite multiverse with all its complications isn't really simpler. The principle of falsifiability, championed by philosopher Karl Popper, suggests that scientific theories must be testable. Some argue that eternal inflation and the multiverse aren't falsifiable, making them unscientific. Others counter that they do make testable predictions, just not direct observations of other universes. The anthropic principle is another philosophical concept that's become central to modern cosmology. It comes in two forms: the weak anthropic principle, which says that the universe must have properties that allow observers to exist, a tautology, and the strong anthropic principle, which suggests that the universe's properties are somehow constrained by the requirement that observers exist, more controversial. Eternal inflation relies on a version of the weak anthropic principle to explain fine-tuning. There's also the question of what counts as an explanation. If we explain the Big Bang as a quantum fluctuation, we've pushed the explanation back to the quantum vacuum. But then we need to explain the quantum vacuum and the laws that govern it. At some point, we might have to accept that some things are just brute facts that can't be further explained. The debate is about where that point is. Some physicists, like Sean Carroll, argue that we should embrace the poetic naturalism view. The universe can be described at different levels, from quantum fields to human consciousness, and each level has its own vocabulary and concepts. The origin of the universe is best described in the language of quantum cosmology, but that doesn't make questions about meaning or purpose irrelevant. It just means they operate at a different level. Let's also consider some of the historical context for these debates. The Big Bang theory itself was controversial when first proposed. The term Big Bang was coined by Fred Hoyle as a derisive term for a theory he opposed. Hoyle favored a steady-state model where the universe had no beginning. The discovery of the cosmic microwave background in 1965 provided strong evidence for the Big Bang and against steady-state models. Inflation was proposed in the 1980s to solve the horizon and flatness problems. Initially, it was controversial, but it gained support as its predictions were confirmed by observations of the CMB. However, inflation has always had critics, including Roger Penrose and other prominent physicists who question its theoretical foundations. String theory emerged in the 1980s as a potential theory of everything, but it struggled to make testable predictions. The ekpyrotic model was developed as a string theory alternative to inflation. Loop quantum gravity emerged in the 1990s as another approach to quantum gravity, leading to the Big Bounce scenario. The Hartle-Hawking no-boundary proposal was developed in the 1980s and represented a new way of thinking about quantum cosmology. It inspired a generation of physicists to think about the wave function of the universe, but it remains controversial. Each of these developments has built on previous work while also challenging fundamental assumptions. The history of cosmology is a story of successive approximations, each one capturing more of the truth while revealing new mysteries. Let's talk about some of the mathematical techniques that are used to study these theories, because the math is what makes them precise. The Friedman equations, which describe the expansion of the universe in general relativity, are the starting point. They relate the expansion rate to the density and pressure of matter and energy. When you trace them back in time, you get the singularity. Quantum cosmology modifies these equations. In the path integral approach, you use a mini-superspace approximation. You assume the universe is uniform and only vary the scale factor and maybe a scalar field. Then you calculate the quantum amplitude for different histories using the Feynman path integral formula. The Hartle-Hawking wave function is a particular solution to the Wheeler-DeWitt equation, which is the quantum version of the Friedman equations. In loop quantum gravity, you use different variables. Instead of the metric, you use a connection and its conjugate triad. The quantum states are described by spin networks, which are graphs with edges labeled by quantum numbers. When you apply this to cosmology, you find that the Wheeler-DeWitt equation becomes a difference equation instead of a differential equation because the geometry is discrete. This leads naturally to a bounce. In string theory, you use extra dimensions and branes. The dynamics are described by higher dimensional generalizations of Einstein's equations, with additional fields like the Delaton and Raman-Drummond fields. The ekpyrotic model uses these to describe brane collisions. Each of these mathematical frameworks has its own beauty and challenges. The path integral approach is elegant but hard to define rigorously. Loop quantum gravity is mathematically precise, but hard to connect to low-energy physics. String theory is rich and powerful but has too many solutions, the landscape problem. The experimental challenges are equally daunting. The Planck energy scale is about 1019 GeV. That's 10 trillion times more energetic than the Large Hadron Collider. We're not going to build a particle accelerator that reaches those energies anytime soon, if ever. So we have to rely on cosmic observations. The cosmic microwave background is our best window because it's the oldest light in the universe, coming to us from when the universe was 380,000 years old. But that's still far from the Planck time of 1043 seconds. The patterns we see in the CMB have been processed by 380,000 years of cosmic evolution, so connecting them to specific quantum gravity models is indirect. Gravitational waves offer a potentially cleaner signal because they would come directly from the early universe, unprocessed by later evolution. But they're incredibly weak and hard to detect, especially the primordial background. Despite these challenges, the search continues because the stakes are so high. Understanding the origin of the universe would answer one of humanity's oldest questions and could revolutionize our understanding of physics. Let's also consider some alternative perspectives that challenge the mainstream views. One critique of inflation comes from the philosopher of science David Albert, who argues that inflation doesn't really explain the low-entropy initial state of the universe. He points out that inflation requires a very low-entropy initial state itself. The inflatoned field has to be in a special configuration, so it doesn't solve the problem it claims to solve. Another critique comes from physicist Paul Steinhardt, one of the original architects of inflation who later became one of its most vocal critics. He argues that inflation is not predictive because virtually any outcome can be produced by some inflationary model. He also points out that most inflation models lead to eternal inflation and a multiverse, which makes the theory untestable. He advocates instead for cyclic models that he believes are more predictive. There are also critics of string theory like Peter Woit and Lee Smolin, who argue that string theory has failed to make testable predictions and has become a dead end. They advocate for alternative approaches like loop quantum gravity. The debate between string theorists and loop quantum gravity researchers has been ongoing for decades, with each side pointing to the successes of their approach and the failures of the other. The philosopher of science Karl Popper argued that scientific theories must be falsifiable. Some critics of string theory and eternal inflation argue that these theories are not falsifiable and therefore aren't science. Defenders counter that they do make falsifiable predictions, just not yet testable ones, or that they make statistical predictions about the multiverse that can be tested in principle. There's also a growing movement of physicists who argue that we need to rethink the goals of fundamental physics. Maybe we're looking for a unique theory of everything, when we should be thinking about a framework of theories. Maybe the universe isn't mathematical in the way we think. Maybe spacetime isn't fundamental but emergent from something else, like quantum information. These are radical ideas that are gaining traction. Let's explore the emerging ideas around entanglement and spacetime. There's a growing body of work, particularly in the context of the AD-SCFT correspondence from string theory, that suggests spacetime itself might emerge from quantum entanglement. The idea is that the geometry of spacetime is encoded in the pattern of entanglement between quantum fields. If this is true, then the Big Bang might represent a reorganization of entanglement rather than a singularity in spacetime. The early universe might have been a highly entangled quantum state that, as it evolved, gave rise to the emergent spacetime we experience. This could revolutionize how we think about quantum cosmology. Some researchers are exploring it from qubit ideas, the notion that information is more fundamental than spacetime or matter. In this view, the universe is fundamentally a quantum computer, and spacetime emerges from how information is processed. The Big Bang would represent the start of this computational process. These ideas are highly speculative but show how quantum information theory is starting to influence cosmology. They suggest that the question, what came before the Big Bang, might be reframed as what quantum information pattern gave rise to our emergent spacetime. The answer might involve quantum circuits or tensor networks rather than classical geometries. Let's also discuss the role of dark energy and the future fate of the universe, because this connects to some of these origin theories. We now know that the universe's expansion is accelerating, driven by what we call dark energy. This suggests that the universe will continue expanding forever, growing cold and dark in a big freeze. In the far, far future, all stars will burn out, black holes will evaporate, and the universe will become a dilute gas of photons and other particles. This picture of the future might connect to the origin in cyclic models. In Penrose's CCC, the cold, empty future becomes indistinguishable from a hot, dense beginning through conformal rescaling. In other cyclic models, dark energy causes a period of accelerated expansion that resets the universe for the next cycle. The discovery of dark energy has thus breathed new life into cyclic cosmology. But dark energy is itself a mystery. It could be a cosmological constant, a constant energy density of the vacuum, or it could be a dynamical field that changes over time. The nature of dark energy could have implications for cosmic origins. If it's a cosmological constant, eternal inflation is more plausible. If it's dynamical, cyclic models might be favored. The observational constraints on dark energy are getting tighter. The Dark Energy Survey and the upcoming Vera Rubin Observatory will map billions of galaxies to measure how dark energy has evolved over cosmic time. This could reveal whether dark energy is constant or changing, which would inform our theories of cosmic origins. Let's also consider the possibility that we might need to go beyond quantum mechanics itself. Some physicists, like Gerard Hooft, have suggested that quantum mechanics might be an emergent theory from a more fundamental deterministic theory. In this view, the randomness of quantum mechanics is just our ignorance of underlying degrees of freedom. If this is true, it could radically change our understanding of quantum cosmology. Other physicists are exploring theories that modify quantum mechanics at the cosmological scale. For example, objective collapse theories propose that quantum superpositions spontaneously collapse, which might solve the measurement problem and could have cosmological implications. If wave functions collapse, this might affect the early universe's evolution. However, modifying quantum mechanics is extremely difficult because the theory is so well tested. Any modifications have to be extremely small to avoid contradicting experiments, but large enough to have cosmological effects. This is a delicate balance that most attempts have failed to achieve. Let's also discuss the role of artificial intelligence and machine learning in modern cosmology. As our datasets get larger and our models get more complex, AI is becoming essential. Machine learning algorithms can search for subtle patterns in the CMB that might distinguish between theories. They can simulate complex quantum gravity models that are too difficult to solve analytically. They can help solve the measure problem by identifying statistical patterns in multiverse models. Already, AI is being used to analyze Planck data, looking for non-Gaussianities that could indicate new physics. It's being used to simulate string theory models with different compactifications, trying to find ones that match our universe. It's being used to solve the Wheeler-DeWitt equation numerically in quantum cosmology models. This computational revolution might be as important as new theoretical ideas. Let's also consider some of the crazier but still scientifically grounded ideas that have been proposed. One is the possibility that our universe was created in a laboratory by an advanced civilization. If a civilization could create a black hole, the interior of that black hole could, in principle, inflate to become a new universe. This sounds like science fiction, but it's consistent with our understanding of general relativity and quantum mechanics. The physicist Edward Harrison suggested that this could be a mechanism for universe creation, and Lee Smolin has proposed a cosmological natural selection scenario where universes with more black holes produce more offspring universes. If this were true, it would explain the fine-tuning of physical constants. Universes that can produce black holes might also be conducive to life. But this is extremely speculative and doesn't really solve the ultimate origin question. It just pushes it back to a prior universe. Another wild idea is the clockwork universe, where time is quantized and the universe ticks like a cosmic clock. Each tick could represent a quantum transition between states. This could potentially explain the arrow of time and the origin of the universe in terms of discrete quantum steps. There's also the umbrella universe idea, where our universe is just one layer in a stack of universes, each with different properties. The stack might emerge from a more fundamental theory where dimensions condense or freeze out at different energies. Most of these ideas are at the fringe of theoretical physics, but they illustrate the creative thinking being applied to this problem. When you're trying to explain the origin of everything, you have to be willing to consider radical possibilities. Let's also talk about the psychological and human side of this quest. Why do we care so much about the origin of the universe? Partly it's pure curiosity, the same drive that makes us explore new continents and climb mountains. But it's also about meaning. Understanding where we came from helps us understand who we are and what our place is in the cosmos. For many physicists, this quest is a life's work. They've devoted decades to developing these theories, often with little experimental feedback. It requires patience, creativity, and a tolerance for uncertainty. The debates can get heated because the stakes are high. If your theory is right, you could revolutionize our understanding of reality. If it's wrong, you might waste your career. The community has had to develop ways to evaluate theories in the absence of data. They use criteria like mathematical elegance, naturalness, explanatory power, and consistency with known physics. But these criteria are subjective, which is why there are such deep divisions. Let's also consider the public communication challenges. How do you explain these incredibly complex ideas to a general audience? How do you convey the uncertainty and debate without making it sound like we know nothing? How do you handle the fact that some of these ideas border on metaphysics? Responsible science communication requires being honest about what we know and what we don't. It means presenting multiple viewpoints and explaining the reasons for disagreement. It means avoiding hype and being clear about the difference between established science and speculation. It also means conveying the excitement and wonder of the quest, even in the absence of definitive answers. That's what I'm trying to do in this video. Give you a comprehensive overview of the landscape of ideas, explain the technical details without oversimplifying, and be honest about the uncertainties and debates. Now let's zoom out and think about the big picture. We're living in a golden age of cosmology. We have precise measurements of the universe's composition, about 5% ordinary matter, 27% dark matter, and 68% dark energy. We know the age of the universe to within 1% precision. We have detailed maps of the cosmic web, the large-scale structure of galaxies. We can see almost all the way back to the Big Bang. But the origin question remains open. The singularity problem is unsolved. We don't have a confirmed theory of quantum gravity. The debates between inflation and alternatives are ongoing. The multiverse idea is controversial. The measure problem is unsolved. What would it take to make real progress? Probably a combination of new theoretical insights and new observational data. We need a theory of quantum gravity that can make definitive predictions. We need observations that can distinguish between these models. We might need entirely new conceptual frameworks. Some physicists think the answer will come from a completely unexpected direction, perhaps from condensed matter physics, where analogs of spacetime emerge from quantum systems. Others think it will come from pushing our current theories to their limits, or from finding contradictions that point the way to new physics. There's also the possibility that we might never know. The origin of the universe might be empirically inaccessible, beyond the reach of any conceivable experiment. If that's the case, we'll have to settle for plausible stories rather than confirmed theories. But history suggests that human ingenuity finds ways to test seemingly untestable ideas. No one thought we could detect gravitational waves, but we did. No one thought we could image a black hole, but we did. So there's reason for hope. Let's also reflect on what we've learned even without a definitive answer. We've learned that the universe is far stranger and more wonderful than we imagined. We've learned that our intuitions about space, time, and causality break down at the quantum level. We've learned that mathematics is a powerful guide to reality. We've learned that the quest for understanding is itself worthwhile. We've also learned humility. The universe doesn't owe us an answer. It might be that some questions are beyond our grasp, but the attempt to answer them pushes the boundaries of knowledge and leads to unexpected discoveries. The search for what came before the Big Bang has already revolutionized physics. It's led to inflation theory, string theory, loop quantum gravity, and new ways of thinking about quantum mechanics. Even if we never find the final answer, these developments are valuable. Let's also consider the educational aspect. How do we train the next generation of cosmologists to tackle these problems? They need to be experts in general relativity, quantum field theory, statistical mechanics, and observational astronomy. They need to be comfortable with advanced mathematics and computational techniques. They need to be able to think creatively and critically, and they need to be able to communicate their ideas clearly. The current generation of PhD students in cosmology are learning these tools and developing new ones. They're working on numerical simulations of quantum gravity, developing new statistical methods for analyzing CMB data, and exploring the mathematical structures underlying these theories. They're also learning the history and philosophy of science, which helps them understand the context of their work. The interdisciplinary nature of this field is increasingly important. Cosmologists collaborate with computer scientists, mathematicians, philosophers, and even theologians. They attend conferences across disciplines. This cross-pollination is essential for making progress on such deep questions. Let's also talk about the funding and institutional aspects of this research. These are big science questions that require large collaborations and expensive experiments. The Planck satellite cost over $1 billion. The Simons Observatory and CMB-S4 will cost hundreds of millions. The Large Hadron Collider costs billions. This requires society to value pure research with no immediate practical payoff. The justification is that understanding the fundamental nature of reality is a central human endeavor. It satisfies our curiosity and has historically led to unexpected technological advances. General relativity gave us GPS. Quantum mechanics gave us computers. Who knows what quantum gravity might give us? Even if it never has practical applications, understanding our origins is valuable in itself. The political realities are challenging. Funding agencies have to balance different fields and approaches. Theoretical physics, especially speculative areas like quantum cosmology, faces pressure to demonstrate relevance. But history shows that the most profound advances often come from pursuing questions for their own sake. Let's also consider the role of international collaboration. Cosmology is a global endeavor. The Planck satellite was a European Space Agency mission with contributions from NASA. The Simons Observatory involves scientists from dozens of countries. The Large Hadron Collider is a truly international facility. This collaboration is essential, but also creates challenges with funding, governance, and coordinating across time zones and cultures. The COVID-19 pandemic has also affected this research. It's disrupted experiments, delayed conferences, and made collaboration harder. But it's also accelerated the adoption of virtual tools and shown that science can continue even under difficult circumstances. Now let's think about what would happen if we did find a definitive answer. Suppose we discover definitive evidence for eternal inflation and the multiverse. That would mean our universe is just one of infinitely many, and the laws of physics are environmental rather than fundamental. This would be a profound shift in our worldview. Or suppose we find evidence for a big bounce from loop quantum gravity. That would mean the universe is much older than we thought and perhaps cycles forever. It would suggest that spacetime is discrete at the most fundamental level. Or suppose the no-boundary proposal is confirmed, and we discover that time is emergent. That would revolutionize our understanding of causality and perhaps even free will. Each of these possibilities would have implications beyond physics. They would affect philosophy, theology, and our understanding of our place in the cosmos. They might inspire new art, literature, and ways of thinking about meaning and purpose. But they would also raise new questions. If there's a multiverse, can we ever know its full extent? If the universe cycles forever, does this change our understanding of time and eternity? If time is emergent, what does this mean for our experience of consciousness? The discovery of a definitive answer would be just the beginning of a new phase of inquiry. Science is recursive. Each answer raises new questions. Let's also consider the possibility that the answer might be something we've never imagined. The history of science is full of examples where the real answer was more surprising than any hypothesis. No one predicted quantum mechanics before it was discovered. No one predicted dark energy. The universe has a way of surprising us. The origin of the universe might involve concepts that we don't yet have the mathematics to describe. It might require a new conceptual framework that we can't even imagine from our current perspective. This is why keeping an open mind and pursuing diverse approaches is so important. Let's also reflect on the human stories behind these theories. Roger Penrose, now in his 90s, continues to champion his cyclic cosmology despite widespread criticism. His persistence is admirable, even if most physicists disagree with him. Alan Guth, the father of inflation, is still active and continues to develop and defend the theory he created over 40 years ago. Paul Steinhardt, who helped develop inflation, had the intellectual honesty to become one of its most vocal critics when he became convinced it didn't work. Andre Lind, one of the most creative theoretical cosmologists, has been developing inflationary models for decades and remains optimistic about their prospects. Carlo Rovelli, one of the founders of loop quantum gravity, has spent his career developing an alternative to string theory and remains convinced it's the right path. These are people who have dedicated their lives to understanding reality at its deepest level, often without the satisfaction of experimental confirmation. Their stories are inspiring examples of intellectual courage and persistence. Let's also talk about the role of public engagement. Videos like this one, popular science books, public lectures, and social media have brought these ideas to a broad audience. This is important both for inspiring the next generation and for maintaining public support for fundamental research. But it also creates challenges, as speculative ideas can be presented as established fact. That's why it's crucial to be clear about the status of different ideas. Inflation is well supported by evidence but has unresolved issues. Eternal inflation and the multiverse are plausible extensions but remain speculative. Cyclic and ekpyrotic models are interesting alternatives but face significant challenges. Loop quantum gravity is a promising approach to quantum gravity but is still developing. The no-boundary proposal is elegant but mathematically problematic. CCC is largely ruled out by observations. Quantum fluctuation models are intriguing but hard to test. Being honest about this uncertainty is essential for maintaining scientific credibility. The future of this field depends on both new ideas and new data. On the theoretical side, we need a better understanding of quantum gravity. String theory and loop quantum gravity both offer frameworks, but neither is complete. Some physicists think we need a completely new approach, perhaps based on quantum information or something else entirely. On the observational side, we need more precise measurements of the CMB, better gravitational wave detectors, and new ways to probe the early universe. The next decade will be crucial as new experiments come online. There's also the possibility that we might need to accept a more pluralistic view of cosmology. Perhaps different theories apply in different regimes, or perhaps they're all approximations to a deeper theory we haven't found yet. The history of physics suggests that, when there are multiple competing theories, the resolution often comes from a new idea that synthesizes or supersedes them. Let's also consider the possibility that we're asking the wrong question. The question, what came before the Big Bang, assumes that time and causality work at the cosmic level the way they do in our everyday experience. But this might be a category error, like asking what color sound is. The Hartle-Hawking proposal suggests that time itself loses meaning at the Big Bang. In loop quantum gravity, time emerges from the dynamics of quantum geometry. In eternal inflation, before might be meaningless because different universes aren't causally connected. This doesn't mean the question is unscientific. It means we need to be careful about what we mean by before. In relativity, before and after depend on the observer. In quantum mechanics, causality is probabilistic. In quantum gravity, our intuitive notions might break down completely. Perhaps the question should be rephrased as, what explains the initial state of our universe? Or, what is the fundamental quantum state of the cosmos? These are more precise and might be answerable even if before turns out to be meaningless. Let's also discuss the connection to other fields. The origin of the universe is connected to the nature of time, which is also studied in philosophy and psychology. It's connected to information theory, which is studied in computer science. It's connected to the foundations of mathematics. Some have suggested that mathematical logic might constrain which universes are possible. This interdisciplinary nature is both a challenge and an opportunity. It means cosmologists need to learn about fields outside physics, but it also means insights from other fields could be crucial. The holographic principle emerged from string theory, but has influenced quantum information theory. Ideas from quantum computing might help solve problems in quantum cosmology. The brainpower being devoted to these questions is extraordinary. Thousands of physicists around the world are working on theoretical models, analyzing data, developing new mathematical tools, and building new experiments. The collective effort is immense. But there are also concerns about the health of the field. Some worry that physics has become too speculative, disconnected from experiment. They point to the failure to detect supersymmetry or extra dimensions at the LHC and the difficulty of testing quantum gravity theories. They worry that physicists are chasing mathematical beauty rather than empirical truth. These concerns are valid and have sparked important debates about the direction of the field. Many physicists are calling for a renewed focus on testable predictions and a more critical attitude towards speculative theories. Others argue that we need to be patient. These are hard problems that will take time to solve. The field is also grappling with issues of diversity and inclusion. Like many areas of physics, cosmology has historically been dominated by men from certain geographic regions. Efforts are underway to make the field more welcoming to people of all backgrounds, because diversity of perspective often leads to better science. Let's also consider the role of education and outreach. Programs like the International Masterclass in Cosmology bring students from around the world to learn about cutting-edge research. Online courses, popular books, and videos like this one democratize access to these ideas. The hope is to inspire the next Einstein, who might come from anywhere. The ultimate goal is to understand our place in the cosmos. We're not just trying to solve abstract mathematical puzzles, we're trying to understand our origins and our destiny. This is a profoundly human endeavor that connects to our deepest questions about meaning and existence. As we wrap up this cosmic journey, I want to bring it back to you. Yes, you watching this video right now, wherever you are, whatever time it is. Whether you're watching this at 3 a.m. because you can't stop thinking about these questions, or during your lunch break at work, or with your morning coffee as the sun rises, in this moment, we're connected by our shared wonder at the cosmos. Every theory we've explored today, from the infinite multiverse of eternal inflation to the discrete spacetime atoms of loop quantum gravity, from the cosmic cycles of Penrose to the timeless emergence of Hartle-Hawking, they're all attempts to answer a question that you and I both asked the first time we looked up at the stars and wondered, where did all this come from? And here's the beautiful thing. We might not know the answer yet, but we're asking the question. We're using the most powerful tools of mathematics and science to peer back to the very beginning of time and space. We're building machines that can detect gravitational waves from the dawn of creation. We're writing equations that might describe the quantum geometry of the cosmos. We're having fierce but respectful debates about what counts as evidence and what makes a theory scientific. We're doing science at its best. The fact that we can even ask, what came before the Big Bang, is a testament to how far we've come. For most of human history, this wasn't even a question people could formulate. Now it's a research program pursued by thousands of brilliant minds worldwide. Whether the answer turns out to be eternal inflation, a big bounce, conformal cycles, a quantum fluctuation from nothing, something we haven't thought of yet, or perhaps something we'll never fully know, the journey of discovery itself is magnificent. Each theory we've explored is a window into reality, showing us different facets of how the cosmos might work. Even the theories that turn out to be wrong are valuable because they teach us what doesn't work and point us toward what might. The next decade will be exciting. New experiments will test inflation's prediction of primordial gravitational waves. Loop quantum gravity will make more precise predictions about gamma-ray bursts. String theory might find a home in the data from the LHC's successors. Quantum computing might simulate quantum cosmology models we can't solve analytically. And who knows? Maybe a brilliant young physicist watching this video right now will have the key insight that unlocks the mystery. If you found your mind bending, your imagination soaring, and your curiosity piqued, then I've done my job. If you're feeling a bit overwhelmed, that's okay. These are the hardest questions in science. Take some time to process, maybe rewatch parts of this video, dig into the references in the description, and join the discussion in the comments. Your questions and insights add to the conversation. Before I say goodnight, I have a couple of asks for you. If you appreciated this deep dive into cosmic origins, if you think videos that respect your intelligence and don't shy away from complexity are valuable, please hit that like button. It tells the algorithm that thoughtful content deserves to be seen, and it means the world to me. If you're not subscribed, consider joining our community of cosmic explorers. We're going to keep diving deep into the biggest questions, and I don't want you to miss what's coming next. Ring that notification bell so you know when our next journey begins. And here's what I'm really curious about. I want you to comment below with two things. First, which theory of cosmic origins resonates most with you? Are you team inflation, team cyclic, team multiverse, team loop quantum gravity, or are you holding out for something completely new? And second, tell me where you're watching from and what time it is. I love seeing comments from every corner of the planet, from sunrise in Tokyo to sunset in Sao Paulo, from middle-of-the-night stargazers in rural Idaho to lunch break watchers in London. You make this community truly global, and I read every single comment. Look up at the sky tonight, wherever you are. Those stars, that moon, the planets you might see, they're part of a story that stretches back 13.8 billion years and maybe much further. You are part of that story. The atoms in your body were forged in the nuclear furnaces of stars that lived and died long before our sun was born. Your consciousness is the universe's way of understanding itself. And right now, in this moment, you're participating in humanity's greatest quest, to understand where we came from and what it all means. So as you go about your night, whether you're heading to bed or just starting your day, carry this with you. We live in an extraordinary cosmos, and we have the extraordinary ability to ask why. That might be the most wonderful thing about this whole story, not that we have the answers, but that we can ask the questions. From wherever I am to wherever you are, I'm sending you cosmic wishes for clear skies, curious minds, and the courage to keep asking the big questions. Good night, fellow traveler. Sleep well under the same stars that have inspired wonder in every human who ever lived. And remember, the universe is not only stranger than we imagine, it's stranger than we can imagine. But that won't stop us from trying. Thank you for joining me on this journey beyond the Big Bang. I'll see you next time.